Hello, my name is Joshua Fair, and I am taking Physics 2211 at Georgia Tech, and this is my lab video. This lab is about determining oscillations from a spring model and comparing that with an experimental model. Now, this lab discusses four key topics. The first being Newton's second law, which states that an object's acceleration is dependent on the net force being applied to an object and the mass of that object. Spring and gravitational forces determine how much force is used on an object in relation to the spring or the gravitational body nearby it. Potential energy is the energy stored up in an object. And the energy principle states that an object cannot create or lose energy, it is always transformed. Now, the purpose of this lab was to investigate the motion of a mass oscillating vertically on the spring and compare the results of a computational model. On the left, there is a model of a compressed and stretched spring with a mass hanging off of it. This is similar to the experiment, as the system is itself, with the surroundings being the spring and the air. On the right, there are a few equations. Well, more than a few, but the first is Newton's second law, uh, followed by the position and velocity update formula, as seen here, which is then followed by Hooke's law, and the potential spring energy, as is shown here, followed by the potential gravitational energy, and by kinetic energy. All of these formulas will be used in the code that will follow. Now, before I go over the code in details, the computational model itself produced this data once it was finished running, using the equations from the previous slide to determine position and compare it to the experimental value, and also to calculate energy. As you see here, this is the position, and this is the energy graph. I'll go over these in more detail later. Now for the experimental video itself, as recorded in Tracker. Now, as the video shows, a man is dropping the mass itself from a spring, and it swings back and forth. This motion was tracked on the right with the position graphs in the x and y direction shown. This experimental data was collected. I went to create the model itself using Glowscripts. This particular section shows the initial conditions that will be used to create the model itself, with the ball mass and initial position being recorded in particular, as shown here. In addition, the spring constant and relaxed length from the spring was also calculated and will be used in the code following. Now, following the creation of the initial conditions, I was able to create the main section of the code. The code uses all of the formula listed on the previous slides to calculate both energy and model position in the x and y directions. As you see here, we're able to calculate position, and then we use this to calculate kinetic energy, gravitational energy, and spring potential energy, as you see in here. Now for the experimental video itself. Now, as shown, the spring rotates at the top in an oscillating direction, followed by the graphs that I demonstrated earlier. This model shows them in creation as it's going throughout. As you see, the spring keeps oscillating. Now for a closer look at the graphs. Shown is the model energy graph, which calculates how much energy the mass and spring had across the time. Delta K represents kinetic energy, delta U grav represents gravitational energy, delta U spring is spring potential energy, and delta E is all the energies combined together and shows the final value. All of these energies I demonstrated their formulas earlier, and this is the graph itself. Now this is followed by the model position in the x and y directions compared to the actual experimental condition. Now the experimental position is kind of wonky, as you see here, with a lot of curves and ups and downs, and this is likely due to me messing it up in Tracker with my clicks, probably a mouse error. So what does it mean? For your model system, is the energy principle satisfied? Well, the energy principle simply states that all energy and work should be equal to one another once complete, as energy is neither destroyed nor created. Now, this is shown by the flat orange line. Since it is flat and equal to zero, that means energy remains consistent throughout the equation and no energy interferes or is input into the system. Now, using the data you obtained in Tracker, make two separate estimates of oscillation pyramids. As you see here, x position and y position are calculated for 4 oscillations. And since they are slightly different from each other, this will likely have an impact on formulas that use period to calculate their endpoints like spring constant. Thank you.